With OpenAI's custom GPTs, we can already fire up a RAG system in minutes. Why sweat over building your own RAG pipeline? Well, today we're going to go through some advanced techniques for RAG that will make your system more scalable to large knowledge bases and also give you more control over how it performs. We will be using Llamaindex as the wrapper code. In the first step, we're going to be looking at some diagrams so you can get a high-level intuition for how everything works conceptually. Then we'll dive straight into the code. This is the diagram we're going to be going through today. It starts with your own knowledge base, and it goes through how we load it in, how we parse it into nodes, how we index it, create a permanent store. This query engine then runs the semantic search to return the relevant pieces of knowledge back to the LLM, and finally feed it back into an answer that is augmented with your own knowledge. Let's zoom in here. So let's say you have a knowledge base with different directories, and in each directory there are files. We would first use the Llama Hub data loader to load them into document objects. And Llama Hub actually supports a lot of different data types. This is just an extract from llamaHub.ai website. You can be pulling information in from your database, from Discord, Notion, and of course like PowerPoint files, PDF files. After you've loaded your documents into document objects, you'll need to parse them into separate nodes or chunks if you like, and then turn each chunk into an embedding, which is a representation of the meaning of that chunk of text in the form of a string. If you use the OpenAI embeddings API, your embeddings will be a list of 1,536 numbers. If you use other embedding methods, there are open source models, lots of different options out there. That list of numbers could be a different length. Some people might wonder, why don't we pass just all of the knowledge into the LLM and have it figure out which bits to use? Theoretically, you can, but you are limited by the context window. And for GPT-4 as well as Gemini, the context window is 32,000 tokens. And for GPT-4 Turbo, it's 128,000 tokens. But even if you can fit everything into the context window, it will still cost you money per token. What people tend to want to do is not to pass in things that is completely irrelevant to the question that is trying to answer. In a vanilla RAG model, we might just chop it up into chunks like this. But in fact, in advanced RAG techniques, there are more effective parsing techniques that you can play around with. For example, just as an easy one, you can have chunks that overlap with each other. You will not only define the chunk size, but also the degree of overlap. If your piece of information just happens to sit at the intersection between two chunks, there is actually a chunk that will return the most relevant piece, as opposed to having to return two chunks or having a piece of it being chopped off. The second solution is to do sentence window retrieval. Here, each sentence gets its own embedding. You could think of it like you're doing a semantic search at a more granular level by comparing sentences. But once you find a hit, instead of only returning that sentence, you will define some window around it, which you will return to the LLM. You could say X number of tokens before and after will be taken as the window, or you can define it by number of sentences before and after. This has the benefit of having more precision in the embedding and the semantic search, but at the same time grabbing the context around that hit to give back to the LLM. And finally, this is another idea around hierarchical automerge retrieval. The idea is that you might have a parent document, and inside the parent document would be a chapter, and then within that chapter there could be chunks. And if you have two chunks within a paragraph that is a hit, then you might want to return the whole paragraph as opposed to just returning these two chunks, as it implies that that whole section of the document is relevant. In essence, end up having some kind of tree structure where you have the top level of the tree as the parent, And then you have a next level of the tree, and then finally you have the leaf nodes. And if there are more than a certain number of leaf nodes that are hits, then you will go up one level in the tree to return the entire parent of those children nodes. Depending on the size of your knowledge base, the creation of this vector index could take some time, as you need to turn every single chunk of text into an embedding, or in fact every single sentence into an embedding, depending on what kind of node parsing strategy you go for. What you want to do is to create a persistent store for this index, so you don't have to recreate it every time, and you'll only need to add to it if you're adding documents into your knowledge base. There are many different ways of doing this. The more permanent ways would include storing it into a vector database like Chroma or Pinecone. And in our code base, we're actually doing it with a quick and dirty method, simply by saving it as JSON files locally. And this technique is great for if you're prototyping and want to quickly be able to test how well your system works before having to think about spinning up a vector database. And using Llamaindex, it will help us save these JSON files into a number of different documents. And you'll be able to see this in our code in a second. And there are two documents that are particularly useful. The first one is called a doc store, where if you go into the schema, you will have an ID for each node. And then within that is a dictionary containing lots of metadata, plus the actual text that was converted into an embedding, as well as the window, which could be a larger context around the embedding text that would be returned to the LLM. And you also have some metadata and also some reference doc information, which breaks down into each of the document has an ID, and then within each of these documents, there's a full list of nodes that belongs to that document, as well as simple metadata like file name, etc. And then in this other document called a vector store is really important because it's the one that contains all the embeddings. So there's a field called embeddings dix. So it's a dictionary of node IDs with their corresponding embeddings. When you run the semantic search, you will be looking through these embeddings to find the most similar one, and then you'll be able to look up the node ID, and then from this other document, be able to retrieve the window that is needed to be passed back to the LLM. After you've stored it into a persistent storage, every time you want to use it, you can just simply retrieve it and bring it into a query engine tool. And you can design your query engine tools by packaging the knowledge bases into different tools. And so when you come to actually spinning up your query engine, you can pick and mix from these different query engine tools depending on what access you want to give the user. When the user comes in with a question, using the same embedding model, the question would be turned into an embedding. And then through a cosine similarity search of your index, you will end up with a bunch of search results that brings back the embeddings within your vector database that is the closest match to the question. As part of your retrieval strategy, you can decide whether you have a greedy search, so just take the first one that is the closest match, or you want to pass to the LLM the top K hits. It could be a K of 3, K of 5. So it's just a trade-off between the tokens that you're using and the amount of information that the LLM has access to. In this diagram, we've shown the sentence window retrieval method. So the hit was for a sentence, and then we're actually bringing back the whole window around that sentence to pass to the LLM. And so this retrieved chunks plus the question gets passed back to the LLM, with which it will derive its final answer back to the user. That's a big picture of how everything comes together. There is a technique called reranking. What reranking does is to take the actual question and each of these chunks and pass it through the LLM to get a revised ranking for which of these are really relevant. And because it hasn't been compressed into an embedding, the thesis is that this would provide a more relevant ranking. And then using that re-ranked search result, we would then choose the top K and then complete that retrieval process. Now that you have a good overview of all of these different steps, let's dive into the code. I will share this link below in the descriptions. This is a Google Colab notebook. Before we dive into the details, let's just go through the key steps. Obviously, the first step would be to install all the prerequisite packages and importing them. Step 0 would be putting in our API keys. Step 1 is to fetch the data from the internet and store it into our local directory. And then we will load those files into the document object. And step 2b is optional, which is just printing stuff out from the documents objects just so you can see what's in it. Step 3 is to parse that document object into nodes and indexing it. We will do 2 versions here. One is the base one, which is the basic chunking strategy. The second one that we will do is a sentence window method. The 4th step is to save all of this into persistent storage. You would only need to do steps 1 to 4 the first time. In the future, once you've saved it to persistent storage, you can just go straight to step 5 to retrieve it from storage. And from that, create your query engine. And then step 7 is just to use it. We've set up a test for step 7 that really shows you the difference between using the base parsing method and the sentence window method. All right, as I mentioned, we install our packages, and there are some packages, and also down here as well, are not things that you essentially need for the rest of this code, but they were useful when I was testing some other stuff, so I just left it in there. Importing a bunch of stuff that we're gonna need. Then my keys hidden here. You should put your keys here from OpenAI. And of course, if you're using a different model, then you wouldn't necessarily need that. To create our reg system, we're going to use 2 open source books from the Gutenberg.org website. And I've chosen these 2 very long books. So this one, let me just zoom in a bit. It's a very old book from the 1800s about tea. It's history and mystery. And you can see here it's a very long book. If you go on that website, there'll be different formats of this book. There's PDF, there's ebooks. I've chosen to use the TXT version. And then just to show you that the pipeline works with more than one data source, here's the second one, which is a history of China. And again, super long. Okay, here we're making a directory, my data, and pulling these 2 files directly into our local directory here. Just give it a little bit of time. You can see here, just ignore everything else. My data is a new directory that we created. We've just fetched those files directly off the internet and saved it here locally so we can use it in the next step. So step 2 is to load these 2 files into the document object. Here we're using the simple directory reader and then pulling in all the files inside the My Data folder and loading it into a documents object. Optionally, if you're curious about how it's being pulled in and how it's stored, you can just print out this cell. It will tell you that the length of the documents object is 2, so it's a list of 2, so 1 object per file. The document object includes a document ID, no embeddings right now, the file path, the file name, what kind of file type it is, the size of the file, creation date, the hash of the document, and then the text field here would include the entire book with the line breaks indicated by /n. So yeah, that really goes on for a long time. And if you wanted to see the metadata more clearly, you can see it here. All right, so now that we have the data stored inside these document objects, we can do the node parsing and the indexing. In step 3, we will take those document objects and parse them into nodes and then index them. Here we have 2 different ways of parsing the nodes. The sentence node parser, where we have defined a window size of 3, meaning that the sentence itself plus 3 sentences before and after it will be returned under a key called window. We will also, for comparison, have a base node parser where we're just chopping the document into chunks in the simplest way possible. And here we've defined our LLM as being the OpenAI GPT 3.5 Turbo model. And here we are creating a set of nodes using the sentence node parser from our documents object and creating another set of nodes that we're calling base nodes using our base node parser, which is just a basic chunking strategy. And if we have a look at the 100th node, just so I'm skipping over all of the titles and the table of contents, and print that out, and you can see the difference. In the sentence node, you have a node ID and just a single sentence as the text that will be converted into embeddings. And for the base nodes, you can see that likewise you have a node ID, but the text is a much longer chunk, and you can see that being truncated here. Now, if we print out this node in more detail, you can see everything that's in this node. Here you have the node ID, and because we haven't done the indexing yet, there's no embeddings here. Here is the window if the sentence is a hit. So the original text is a single sentence. We have no desire to show that China's history is blah, 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 blah. So that's one sentence. If the user's query's embedding is close to the embedding of the sentence, then this whole window will be passed back to the LLM. You can see this sentence being embedded in the middle of this block here. Inside this metadata, you can also see information such as the starting here. So within that document, where the sentence starts and where the sentence ends, this part also captures the relationship of the nodes before it and after it and the parent node. Now, if we change this to base nodes, we can have a look at the difference. You'll see this beginning part is much simpler. It's likewise has the node relationships, has the starting index, ending index. The text is a big block. It's even bigger than the window of the sentence node. Now that we've looked into those nodes, we can create the vector stores. This CTX sentence and CTX base is what's called a service context configuration. So it is here that we're defining which LLM we want to use, which embedding model we want to use, and what is our node parser. And then we will pass these two things into this vector store index here. And we're doing it twice because we're doing it once to create the sentence window version of the index, and then we're doing it again for the base index. Once that's done, you will want to save it into some kind of persistent storage. And there are many different ways of doing it. In our case, we're just going to be saving them as local JSON files under these directory headings. So we'll just let that run for a bit. After that's done, and after we run this, you will see two folders in your Colab file space. Base index, you've got a bunch of files, and sentence index, you've got a bunch of files. And this is where your indices are stored. If you're not using the enterprise version of Colab, your files will not be retained. You might want to download both of these onto your own computer for backing up. When you open up Colab again next time, you don't have to go through steps 1 to 4. You can just go straight onto step 5. You can upload your files onto here and just retrieve it from storage. Once you've retrieved it from storage, you can now create your query engine. Well, here we're doing it twice. So we've got the sentence query engine. We've set the similarity top K to 5. This means that we're taking all of the top 5 closest hits to the user's query and passing all of that into the LLM context window. For the base query engine, we're doing the same thing, but we don't have to define this window key because we're just passing the text that was converted into embeddings as the text that goes into the LLM. Now, finally, we've got all of that set up. We can use it. Now, we've posed a kind of tricky question, and it's deliberately phrased this way for a reason. Let me just read it. Something happened in the United States 10 years after the first American ship sailed for China, which could have made it more expensive to purchase tea. What happened that year? Try to break down your answer into steps. Well, we've deliberately phrased the question this way because it actually needs two different pieces of information. One is at the beginning of the book and one towards the end of the book. We're trying to see whether it can retrieve information from the relevant areas of the book to actually piece together an accurate answer. This part, 10 years after the first American ships sailed for China. So it would first need to figure out when did the first American ships sail for China, and then calculate what is 10 years after that. And then it will have to figure out what happened during that year that could have caused the tea prices to increase. Now let's have a look at the actual document. Here you can see here we're at the very beginning of the document, and it says the first American ship sailed for China in 1984. So it needs this piece of information, and then it needs to add 10 to it. So 1794, something happened in 1794. So let's search for that. Okay, now you can see we're at towards the end of the document, and it says the first duty levied on tea by the United States was in 1789, blah, blah, blah. And then in 1794, however, the rates were increased 75% on direct importations and 100% on all teas shipped from Europe. So the correct answer is that taxes were levied on tea during that year. Let's go back and see if our base query engine can answer this question. So the first American ship sailed for China in 1784. It got this part correct. But something happened in the United 10 years after. To find out what happened that year, we need to look at the information provided in the context. But it did not give us the answer. However, when we use the sentence response, we can say the first American ship sailed for China in 1784. In 1794, so we can see that it understood that it needed to add 10 years to this number. The rates of duty on tea were increased by 75%. So it exactly brought back the correct piece of information we need to answer the question. Therefore, 10 years after blah, 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 the United States increased the rates of duty on tea, which could have made it more expensive to purchase tea. You can see with this experiment why sentence window strategy might be more effective for answering this kind of retrieval task. There are many other strategies, as we've talked about at the beginning of the video, that you can play around with data to see which is the best fit for your knowledge base.